Welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host today. Today, we're presenting Applicability of Hydrodynamics in Large and Small Systems by Victor Ambruş. Victor is currently a faculty at West University in Timişoara in Romania. He got his bachelor degrees in physics and math at the West University in Timişoara, and his PhD in 2014 at the University of Sheffield in the UK. Victor is a world expert on quantum field theory on curved space, relativistic kinetic theory, and lattice-Boltzmann methods and its applications. So today we will hear about a quantitative criterion for the applicability of hydrodynamics, something he has been working on recently. So remember, you can ask questions over email, through our YouTube channel, or Twitter, or any social media that you are following us, and then the questions will be read at the end of the talk. So without further ado, we will turn the time to Victor. And again, Victor, thank you for joining us.
Thank you very much, Alejandro, for the introduction and especially for the invitation to give this presentation. I really appreciate the effort that everybody is putting into keeping this YouTube channel going and delivering in this series of webinars on physics. And I'll be happy to give my contribution on applicability of hydrodynamics in large and small systems. So this is what my slides would actually look like. I'm sorry that my skills in making slideshows do not match those of the artwork shown previously. But essentially, I will go through some works that I've done in this field with several collaborators. It's a summary here, which is not extensive. There are some papers that I didn't mention here. And at the same time, I try to do justice to other people who have worked in the field and to give as broad overview as possible the things I will be talking about. This is the outline. So in the introduction, I will simply try to motivate why relativistic hydrodynamics is a thing and why it's worth looking into this kind of field. Then I will sort of specify what relativistic hydrodynamics really does and what the role of relativistic in front of this this term actually means. And then I'll go to my favorite part, which is kinetic theory. And this kinetic theory will serve as a baseline with respect to which one can discuss about applicability of hydrodynamics. Finally, the applications where I've been working on are on quark-gluon plasma modeling. And I will show you several scenarios where these two theories, hydrodynamics and kinetic theory, can be compared one to the other, and how applicability limits can be formulated for hydrodynamics. I would like to advertise from the beginning that for some of the applications I will be showing, I have actually posted the codes online. And therefore, at the end of the talk, there will be a slide about code availability. For those of you who are keen to download the code, have a look, maybe test it or adapt it to your own needs. It's open source and it's made in such a way that you can compile and run an automatic script that generates all the data files and all the plots that are shown in the corresponding paper. So with that being said, I will jump straight to the introduction. And I have here a collection of various systems and applications where hydrodynamics has to be employed in the relativistic regime. These applications are taken mostly from this very good review by Marty and Müller, two GR physicists that have worked extensively in numerical methods in general relativity. And this is a leading review in computational astrophysics paper. So where do we find them in astrophysics? Of course, for this, we need immense amounts of energy, which are being released and which are being transported in some medium, which behaves like a fluid. So one example, which is mentioned in this review, requires relativistic magnetic hydrodynamics, and it refers to structures which are known as kiloparsec scale jets. So these are jets which are sent out from various structures, either accreting massive, supermassive black holes or similar systems. And they extend over length scales which are comparable to galactic scales. Here we have another example of general relativistic hydrodynamics, where one studies the dynamics of a fluid in a curved space-time, so truly curved. And the reason why this is general relativistic is that here where there's a bit missing from this plot is actually a black hole horizon. So here we have an accretion disk, and the idea is to test the wind which is sent out from the black hole, that you can see here represented as this blue stripe. So of course this is the region, this is the disk. We have a plunging region where the disk is touching the event horizon of the black hole, and there is some outflow coming from the black hole which is sent out back into space. Here is another example. It's the gamma ray bursts, which are still mystical phenomena, still unclear what is their origin or the mechanism behind them. But this is the actual plot, which is obtained from a simulation. Gamma ray bursts are intense energy bursts that comprise highly energetic photons, which are either of short duration, so milliseconds, or longer durations, maybe hours. And those that take only a few milliseconds, converting time into distance involves applying the factor c. So that corresponds to roughly 100 kilometers, something like this, which means that the source which sends out this burst must be of a compact star type. And finally, the last one I have in the series of astrophysical examples is the pulsar wind nebula. So the pulsar is a rapidly rotating neutron star which emanates energy through the poles. And as the jet which is emitted from the pulsar travels through the space, there are several things which can happen. So first of all, we know that neutron stars can occur at the end of the life of a massive star which collapses and explodes as a supernova. And therefore, in this case, in this scenario, there is also a supernova remnant surrounding the neutron star. And this remnant is more or less depicted in this photo here, where we have the free expanding ejecta that you can see here. And basically the energy is emitted, or these pulses are emitted from the neutron star, which is left behind in the center. And as these pulses travel through the ejecta, various shock features will develop. And this pulsar wind nebula is basically a hot magnetized bubble, this pulsar wind, which is represented in this area here. So all these examples that I've shown here are extremely complex and require careful numerical methods to simulate them in order to capture the characteristic features that appear, that can vary over multiple length scale orders of magnitude. So now I go to my field, actually, where I'm working on, and that's accelerator physics, and in particular, quark-gluon plasma. So for this, I put here a phase diagram, which tells us well, where we can find the quark-gluon plasma. You can see it's in the top right of this phase diagram, where we have on the right axis, on the horizontal axis, density, baryon density in this case. On the y-axis, we have temperature. And what this represents is the state in which strongly interacting matter resides. If we are at low temperature, then we encounter the usual hadrons, which are, for example, protons, neutrons. These would be the baryons, or some mesons, which comprise regular matter we are used to. But if we increase the temperature very much, then these kind of bound structures will dissociate and will release the color degrees of freedom. Either the quarks, or it will release the quarks and the gluon degrees of freedom, leading to a deconfined state of quarks and gluons called the quark-gluon plasma. We have some ovals here, which depict which region of this phase diagram is probed in accelerator physics or in accelerator experiments. You can see that at LHC, which performs experiments at very high energies, probes a region which is very close to the y-axis. That means almost vanishing baryon density. And this doesn't mean that the system is extremely dilute. What it actually means is that in quantum matter, like we are dealing with here, this meaning of baryon is not something that you can count. We have 1 baryon, 2 baryons, 3 baryons. It's rather a charge, meaning that where the LHC is doing experiments, we have an equal number of baryons and antibaryons. And when we add them up, these numbers cancel each other, and therefore we are close to the point of 0 baryon density. But actually the state is, of course, very dense there. Here we have the relativistic heavy ion collider, which is probing a region in this space of the phase diagram where a critical point is supposed to reside. This critical point is like a mystical being, it's like a unicorn, as it's been conjectured, but pinpointing its location or even its existence has proven extremely difficult, because you can imagine once you smash two ions head on, you will end up with a very messy system, which is very difficult to analyze, and it's very difficult to extract a clean signal that indicates the existence of this critical point. But anyway, it's conjectured, people are looking for it, and basically this motivates billions of dollars or euros investments into new experiments. So, in fact, to come back to the purpose of this talk, I will consider some models, of course, which simplify the problem sufficiently such that one can draw some quantitative conclusions which are not ambiguous because of the complexity of these systems. So this is called the Bjorken model, which says the following thing. We have two nuclei that collide head-on. This is the initial state. These nuclei, usually they are spherical. We imagine them to be spheres. But because they travel at very high speeds towards each other, we have Lorentz contraction. And therefore, they look in the laboratory frame like flat pancakes. So they interact as they pass through each other. They interact, exchange energy, and through hard scatterings, they also deposit energy in a medium which is created between the two nuclei. So this medium is shown here in a particleized version, but in reality, quark-gluon plasma actually can be viewed as almost a continuous medium because of the large number of constituents, a large number of soft gluons, and also quark, anti-quark pairs, and so on. So what happens is the nuclei, some of the nucleons actually smash into each other and get knocked out from the interacting nuclei, but others will just simply pass by each other. These are called spectator nucleons. And what happens is we have this medium which is created in between, which will expand, will be first dragged by the receding nuclei, and also will expand in the transverse direction. And it's this expansion in the transverse plane which will play a central role in what I will be talking about, because it's related to the so-called flow observables. I will tell you later why these are so important. But we have a stage here which is marked as hydrodynamic evolution. And this is the stage where we can be more or less confident that hydrodynamics is a good theory to describe the evolution of the system which is created here. After the system has expanded sufficiently, it becomes dilute, and its temperature decreases, it cools down, and therefore in the phase diagram will go through the phase transition line back into the hadronic phase. This is called the hadronic freeze out, and from this stage on, hadrons simply fly to the detectors where they are recorded event by event by our experimentalist friends. This is a picture which presents schematically in a TZ diagram. So time is on the y-axis, Z is the distance along the beam, so longitudinal distance. What the evolution of the system looks like from the Bjorken model perspective. So what is represented here, these are lines of constant Bjorken time. And what we expect from this kind of systems is that at least in the middle, this is called the central plateau, the properties of the system don't depend on where we are exactly on this, this hyperbola. These are called rapidity slices, delimited by the lines by the dotted lines. So basically, we expect that the properties of the system will be rapidity independent, at least in the middle. So this is the mid-rapidity region. Of course, very far in the rapidity, we expect that there will be some kind of cutoff because the system is finite. But this terminology will appear later. So what happens is, as we move on to higher and higher Bjorken times, then the temperature decreases because we move to the right in this diagram. And eventually, at some point, let's say this green line here, the system has already hadronized and it has fallen apart. So now we get to these transverse plane observables, also known as flow observables. The idea is very simple. Let's consider that we have two lead nuclei that collide, but they collide in a non-central way. We can see that the overlap region is not circular. It is more like an almond shape. And in this almond shape, we have one direction in which the medium is longer, has a larger extension, and another dimension where it's shorter, has a smaller extension, which means that if we think in terms of gradients, so we have basic energy deposition in this almond shape and nothing around it, vacuum, then the gradients along this direction, the horizontal one, will be larger than along the vertical one, which means that the medium is being pushed out in the transverse direction with larger force. And this leads to particles flying out with a higher velocity. So eventually, we end up with a distribution, a particle distribution function, which has more particles traveling fast in the horizontal direction than on the vertical direction. And this kind of elliptic shape that we see in the particle distribution function appears as a signal in this kind of plot. This is a plot of delta phi, this is angle separation, and delta eta, this is rapidity beams. And we see this two-ridge structure. So the two-ridge structure tells us that we have a harmonic function of the type cos of 2 delta phi. And this cos 2 delta phi is what is known as elliptic flow, or the elliptic flow coefficient is the magnitude of the cos 2 delta phi harmonic in the particle distribution function of emitted hadrons. Why this is important? Because in the absence of interactions between the constituents of this medium, so if the medium would be weakly coupled, then this picture here will not generate any harmonics. It's called free streaming if the particles are not talking to each other. And basically, the distribution function will not care about how large the gradients are because there is no interaction between the particles to exchange the shape of the distribution. So long story short, this was a smoking gun observable proposed more than 20 years ago, 30, 40 years ago, but validated experimentally through this kind of experimental result that actually the medium is strongly interacting. And therefore, that confirms that the quark-gluon plasma phase is created in a heavy ion collision at sufficiently large energies, and that this quark-gluon plasma phase is strongly coupled. Okay, so now I take a step back. I will quickly go through relativistic hydrodynamics as a theory. And excuse me for all this notation that you see here, but somehow I felt the need to simply go through it. So first of all, people doing high energy physics don't like to see H bar, C, Boltzmann constant, and so on, because they simply provide clutter in the formulas. Every high energy physicist can always restore these constants by dimensional arguments. So they will be equal to 1 in what follows. Usually in high energy physics, we understand that relativistic energy density is comprised of two components. We have rest mass, which is always dominant because particles are massive and the energy associated with the mass of the particle is very large, and kinetic energy. And this is true only in the case when we have mildly relativistic fluids or mildly relativistic velocities. But if the velocities increase a lot, very much, so the speeds approach the speed of light, then the fluid goes to an ultra-relativistic regime, where basically the mass term here becomes negligible. We'll talk about thermodynamic pressure. And this is basically a property of the fluid, the thermodynamic property, that tells us if the fluid has some temperature and some, let's say, chemical potential or density, energy density, or so on, then it will exhibit or exert some pressure, which is fixed by the equation of state. To characterize the state of motion of the fluid, we have the four velocity, this u mu, which has this form. We have the gamma factor. This is the Lorentz gamma. And here's the three velocity, which is bounded by the speed of light. Often we think in terms of number densities, so that's just the ratio of this mass density that appears here to the mass of the constituents. But as I told you previously, in quantum systems, actually counting particles is not so relevant. And this is because in quantum systems, we always have the possibility of particle-antiparticle pair annihilation or creation. What actually matters and what is conserved in the quantum system is the charge, which gives us particles minus antiparticles. And of course, a way to treat this kind of systems is through the perspective of the parameters of a grand canonical ensemble, temperature, and chemical potential. These are parameters that provide the cleanest description of the system. We then have kinematics in a fluid. So we have the notion of comoving or material derivative, which represents the derivative of some quantity, if it's scalar, vector, doesn't matter, along the four velocity of the fluid. So here we have a time derivative, and here we have a term which takes into account the velocity of the fluid, and this is basically a statement of the fact that the property that we're trying to calculate the derivative of is also tracked by the fluid. So it's not just its variation in time upon its own, it's also how it's being moved by the fluid flow. Okay, here we have the expansion scalar, which tells us if the fluid is expanding. So if it has this kind of inflationary type of motion. And we have the shear stress, the shear tensor, which tells us if two adjacent layers of fluid move at different speeds. So basically, we have adjacent layers on the x-axis, basically, and if they have perpendicular velocities, let's say along the y-axis, which is different, then there will be a non-vanishing shear. Shearing means basically this kind of rubbing motion. So shearing is associated with viscous dissipation as well as expansion. What are the quantities or the structures that we are dealing with to describe relativistic fluids? We need vectors and tensors that have Lorentz indices. So if we think in terms of particle number, then we have number density current, which is given by the particle density multiplied by the four velocity. This is an example of a quantity which is advected with the fluid. Basically, this current tells us that the particles are simply flowing with the velocity u mu of the fluid. Here is the example of a conservation law. If we expect the number of particles to be conserved, then this gradient, this divergence of particle number current will be equal to 0. And then we see here that we have automatically the co-moving derivative of n, which appears, as well as some term which accounts for the expansion of the fluid. From the energy momentum tensor, we have two equations. One is the conservation of energy, which takes this elegant two-term form that we can approximate. So if the fluid is not so relativistic, then we can recover some well-known formulas from non-relativistic fluid mechanics. It's basically the variation of kinetic energy in time. Whereas here we have the evolution equation for the momentum of the fluid. And this is also known as the Cauchy equation in non-relativistic fluids, and it's basically just the material derivative of the velocity. There is also an entropy current, and for a perfect fluid, here there is no dissipation, so this is all perfect fluid. We have the fact that the entropy current must be conserved, meaning that the fluid is isentropic, flows at constant entropy. However, real systems are dissipative, so we have to do something to incorporate dissipation, and that is done by adding all these colored terms here, where we have a diffusion current. Here we have a correction to the pressure. This is the bulk viscous pressure or dynamical pressure. And here we have the shear stress tensor. So now we have some evolution equations for particle number, energy, and velocity with some unknown fields on the left-hand side, which have to be specified. In hydrodynamics, this is done by employing so-called constitutive relations, which look like this. This is the so-called Navier-Stokes level that everybody knows from non-relativistic fluid dynamics, where we simply set the fluxes, this pi mu, proportional to some thermodynamic force. This is expansion, this is shearing, and here it's a gradient of chemical potential. Basically, that's what diffusion means. If chemical potential is not constant, then there will be some kind of exchange of particles. In this case, the entropy current is no longer conserved, but second law of thermodynamics imposes that its for divergence has to be larger than or equal to 0, meaning that entropy must increase as a consequence of thermodynamic evolution or fluid dynamical evolution. The problem that we encounter with this kind of theory, which is a first order theory, not the BDNK, of course, BDNK has found a way around it, is that this set of equations with this constitutive relation substituted here is not hyperbolic and therefore is not causal, meaning that this set of equations will support solutions that permit information exchange with speed larger than the speed of light. So one way that one can solve this is to employ dynamical equations for the dissipative terms. So this is the so-called Müller-Israel-Stewart theory, where we have evolution equations for the dissipative quantities. Here is the Navier-Stokes level that you can see to the left and right of the equal sign. But if we add here the relaxation term, then this is a term which is basically second order in some power counting scheme that I don't really want to go into details. But to be consistent, one has to include second order terms also on the right-hand side of the equal sign. And there are a lot of them. So those people who solve relativistic hydrodynamics on a computer have to deal with all these terms that are written here just in numbers. I don't show them, which is a headache. There is also an entropy current. Also, this will obey the second law of thermodynamics, but we don't need to go into those details. So now I want to shift gears and move to kinetic theory and hopefully convince you that this is a more elegant description of fluids which are far from equilibrium especially, but even compared to second order hydrodynamics. So kinetic theory is basically a mesoscale approach, and it lives in this top right corner. So far, we discussed about macroscopic approach where we look at the densities that characterize the fluid. We could say that actually an even better approach is the microscopic one, where we keep track of each particle which appears here. And this is, of course, possible not of each particle, because usually people group particles into test particles, which account for, let's say, 10,000, 100,000 particles, and so on. But that is almost always suffers from noise, from statistical noise, because once you deal with individual constituents, you will have, of course, this fluctuation of the properties of the fluid. The Boltzmann equation provides a mesoscopic approach where we have a distribution function that lives at x and t in space and time, but depends also on the momentum of the constituents. So we don't look at individual constituents, but rather we look at the distribution of these constituents with respect to their momentum. Where is kinetic theory applicable? So here's Boltzmann kinetic theory. Here's collisionless Boltzmann equation, but of course, collisionless Boltzmann equation means Boltzmann equation with negligible collisions. So one could easily extend this box to all the way to the right. Whereas hydrodynamics is split into several regimes. So Euler equations, this corresponds to a fluid which is extremely strongly coupled. Knudsen here means the Knudsen number, which is a ratio of the mean free path to characteristic length of the fluid domain. So if the Knudsen number is small, then it means that the mean free path is negligible, and that means that particles constantly interact with another particle in the fluid. This means extremely strongly coupled. This is the regime where the fluid is not dissipative, is dissipationless, and corresponds to the Euler equations that extend to some small value of Knudsen. Here is 10 to the minus 3, but of course it depends on how you put the factors in calculating this number. for larger mean free paths, then dissipation becomes important, and we have to apply dissipation that basically Navier-Stokes level, which is applicable, let's say, to a Knudsen, which is moderate, 0.05 or something like this. If we go beyond this, then we have to use extended hydrodynamics equations in this plot. It's basically just a statement of second order hydrodynamics. But even that breaks down in the so-called transition regime. Here, a transition regime means that the mean free path is comparable with the length scale of the system, and therefore equilibration in the fluid is already problematic. So I will address this regime in order to make statements about applicability of hydrodynamics. As I said, we need a distribution function. This distribution function is basically number of particles per unit volume in momentum space. We can say that we use one distribution function to model multiple particle degrees of freedom, for example, spin or flavors if we have like quarks, colors if we have gluons. And for the quark-gluon plasma, a good formula is this one here. We take the gluons, we take the quarks, and we convert them all into bosonic degrees of freedom, behave as if everybody is bosonic, and get this number, 42.25. That would be the degeneracy of the quark-gluon plasma at high temperatures. From the distribution function, we can recover the tensors that I showed at the beginning by integrating over momentum space. So we have the particle force flow here, we have the energy momentum tensor, just as integrals of the distribution function. The distribution function itself is basically orbiting around an equilibrium distribution. This is guaranteed by the so-called H theorem of Boltzmann, who was able to show that entropy is maximized when the fluid is in thermal equilibrium, and the fluid is in thermal equilibrium when it's described by the, let's say, Bose-Einstein distribution. Of course, when the fluid is not in fully equilibrated, there is a deviation of the distribution from this equilibrium, and hydrodynamics is basically applicable in the regime where the deviation is small compared to the equilibrium. What do we have in the Boltzmann equation? We have a deceptively simple advection term on the left-hand side. This K mu d mu Fk means advection of the distribution along the form momentum of the particle, because of course the particle is traveling with its own form momentum and it's advecting its number density with itself. But on the right-hand side, we have the truly complicated part of the Boltzmann equation, which is called collision term. This is given as the difference between a gain and the loss term, which are depicted here. So basically, we take a particle which has momentum k. In the gain term, we have a collision, and after a collision, an outgoing particle has momentum k. Therefore, it's added to this the streamline. And loss term is when a particle with momentum k has interacted and has changed its momentum, and therefore disappears from the streamline. Okay, I won't go into the details here for the sake of time. I want to say that there is one way to evade the calculation of the collision integral at each point in space and at each moment in time, because this is very expensive. It's actually a multidimensional momentum integral, very difficult to calculate, at least at the kinetic level. So therefore, people look for simplifications, and one of them is the so-called relaxation time approximation. What we know from the physics of collisions is that they will drive the system towards equilibrium. So this behavior is the main feature, let's say, of the collision integral, and it's captured through this very simple expression, the relaxation time approximation, where tau is the relaxation time, describing the scale on which the fluid equilibrates. Here we have f minus f0. So basically, as long as the fluid is away from equilibrium, there will be some equilibration happening. And here's some term which is originating from the proposal of Anderson and Whiting 50 years ago. So what happens in this kind of formulation is we gain one parameter, this tau r, which is a function of space and time. And with the help of this parameter, we can achieve from this collision model a given shear viscosity, let's say, a given transport property of the fluid. Of course, we can calculate all the transport properties of the fluid, but all of them will involve the same relaxation time. So basically, we say that these two viscosity coefficients, this is the shear viscosity, this is the bulk viscosity, are not independent of each other because they are both proportional to tau r. And here is a plot of the ratio between bulk and shear viscosities. We see that for the Anderson-Whitting model, we have these lines that are simply decreasing functions of temperature. Whereas for the quark-gluon plasma, this is obtained by some Bayesian analysis of actual simulation results. The shape looks more like this. So in the end, this is a caveat of relaxation down approximations, but you can find in these papers that I'm happy to advertise here an extension called the Shakov model, or relativistic Shakov model, which allows the simultaneous control of both shear and bulk viscosities. So one can surmount this difficulty. Okay, let's go now to the quark-gluon plasma. I will remind you again what this is about. So we have basically ordinary matter. We know that if we zoom in, then we start to see inside this, for example, office chair, some molecules. We zoom in some more, we find atoms. Inside the atom, we find nucleons like the proton. If we zoom in even more, we see the gluons and the quarks. Maybe there's something beyond this. If we zoom in onto the quark, we'll find out it's not elementary, but our best theories so far say that these gluons and quarks, these particles, are actually elementary and have no internal structure. So here's a small depiction of how one achieves the phase transition from regular hadronic matter to the quark-gluon plasma. So if you increase the temperature, then there starts to be thermal agitation there, of course, and also you start seeing particles popping up from the vacuum. And eventually, the boundaries of these hadrons will start to overlap. Similarly, if you increase the density, then you compress the hadrons one towards the other. Eventually, their boundaries will touch and will overlap. And at this stage, boundaries simply dissolve in just hand-wavy explanation of what happens. And we end up with a blob which is comprised of free or released color degrees of freedom. The temperature at which this happens is given for high-energy physicists. 150 MeV is a natural quantity, natural measuring unit. But people who don't work in this field would prefer the Kelvin version. It's 10 to the 12. So that's basically 2,000 billion Kelvin. It's not something you can achieve in your microwave oven at home, but it's something that high-energy physicists routinely achieve in collision experiments. Okay, so here I put a list of solvers that people are using nowadays. Maybe this list is not 100% up to date because last editions were from 2022. But we have hydrosolvers, we have Boltzmann solvers that are particle-based. So basically what I was saying, microscopic approach, but with test particles, not really molecular dynamics, as well as RTA-based solvers. So all these tools have been used. All these tools have their own strengths, fortes, as well as limitations. Hydro has the limitation that it breaks down for flows far from equilibrium. Particle-based solvers have the limitation of statistical noise. So if the system is very close to equilibrium, then the statistical noise tends to be very, very high, and it's decreased by the square root of number of particles employed. So it's really high penalty and becomes very expensive to use close to equilibrium. And RTA-based solvers have severe limitations. Of course, they are not so realistic as particle-based Boltzmann solvers, and have some problems, for example, with non-ideal equations of state. But nevertheless, all these limitations, let's say they have some way of going beyond them, at least to extend the validity domain. So in a nutshell, let me tell you what solver of the Boltzmann equation does. This is the relativistic lattice-Boltzmann solver, which I'm happy to advertise, as it's something that I've been working on as well. First of all, we have to discretize momentum space. So we don't discretize just space and time. We also have to discretize momentum. And this is done by some procedure. So the procedure which is optimal in our opinion, that is Boltzmann people, is if you use Gauss quadratures. Then there are several other tricks which one has to do. So for example, the equilibrium distribution towards which we want to equilibrate has to be replaced somehow by some polynomial representation. Here we have possibility of having force terms in the Boltzmann equation. These have to be, so we can no longer take an exact derivative or symbolic derivative with respect to a discrete quantity. Therefore, we need some suitable expression here. And finally, we need numerical methods which are readily available from hydrodynamic simulations in order to compute the time evolution and to calculate space advection. So the pro of this approach is that we have exact recovery of the moments of the distribution function because of Gauss quadratures, and it's conservative, so one can write all the equations. It's actually easier to write the Boltzmann equation in conservative form than the fluid dynamical equations. The cons is that if we use the polynomial representation of the distribution, then the algorithm breaks down for highly relativistic flows. So if the Lorentz factor is very large. However, this can be solved by dropping the RLB paradigm, that's number 2 here, in favor of discrete velocity models in which we just evaluate this equilibrium distribution directly. And this is what I'll do for the heavy ion collision simulations. So now I want to show you just a quick example of how this scheme, relaxation time approximation with relativistic lattice Boltzmann performs for a classical example, that's the SOD shock tube. So the shock tube is basically a system which has 2 domains, left domain, right domain, separated by some ideal membrane, which is removed at t equals 0. And then the fluid from the left side of the domain will propagate into the right side of the domain as a shock wave. Here are the parameters. Is not a very extreme case, is just one that is able to showcase the main features of the shock. Here is what we expect. So at some time after the membrane has been removed, we have basically the shock front, which pushes matter from the left into the region to the right. Here is some central plateau where density, pressure, as well as velocity have a constant value. And here is a rarefaction wave by means of which matter is taken from the left domain and passed on to the right. So what this plot shows is that the RTA solver that I'm advertising is able to capture the sharp features of the inviscid fluid, so that's dissipationless. And basically you see here that there is a red line, and on top of it is some line with a blue cyan color, which is almost on top. This is the inviscid limit of very small shear viscosity. As we increase the shear viscosity, fluid becomes dissipative, and these features are being rounded. They are being basically made smoother. And on top of everything, we have bumps. Bumps is one of the tools that I was talking about that are particle-based. And bumps basically evaluates the collision integral exactly. So what we're doing in this plot is we're evaluating the ability of RTA to recover physical results obtained by an actual calculation of the collision cross-section, let's say, or of the collision term. Here are several comparisons. So this pressure, this is shear stress. What I want to show here is that hydrodynamics actually will start to have problems. So in the pressure profile, there are no discrepancies. So bumps and RTA and hydrodynamics, which is not shown here, all fall on top of each other. But for the shear stress, what happens is hydrodynamics experiences some glitches. You can see here that this orange line is not on top of the blue and the red line. Blue and red correspond to bumps and RTA. Also here, where this peak is, where the shock is, the shock front resides, there are several artifacts in hydrodynamics. A first hint that hydrodynamics will not perform well very far from equilibrium. And even better, we can see in this kind of plot, here we're looking at the heat flux. Let's compare the RTA with the bumps simulation results. Bumps is noisy, as I told you. It's difficult to obtain a smooth curve from particle-based solvers. But what I want to show you here is that plain RTA, as proposed by Anderson and Wittig in the 70s, basically misses the peak in the heat flux. And it misses the heat flux peak, but captures the shear stress peak, because we have used the degree of freedom of Anderson and Wittig to tune the shear viscosity, which corresponds to the shear stress, but not the diffusion coefficient, which corresponds to the heat. So then comes the Shakov model, and there are several flavors of Shakov models here. And eventually you see that we can reach agreement with bumps. And this is just to tell you that one can do RTA simulations which are accurate even from this perspective. So now I come to the heavy ion collisions. So in a nutshell, as I told you, we have two nuclei that collide. This is the initial state, let's say. Then as we move to time of order of 1 Fermi over C, we have the so-called pre-equilibrium dynamics. Why pre-equilibrium? Because when the nuclei smash into each other, we are basically at this point in the Bjorken diagram or space-time diagram. And here, the receding nuclei are pulling the medium which is formed along the longitudinal direction with very high velocity. So velocity close to the speed of light. And this means that the system will basically, because it's being pulled along one direction, will have a difference between transverse and longitudinal pressures. So the longitudinal pressure in this early stage here is very small because it cannot be sustained by the fluid which is pulled so rapidly along the longitudinal direction, whereas the transverse pressure is the normal pressure of the fluid. So we have a stage here, pre-equilibrium dynamics, in which the fluid starts to build up its longitudinal pressure, and it approaches something which resembles isotropic pressure tensor. Then we have hydrophase. So in this region, hydrodynamics provides a good description of the evolution of the system. Finally, we have hadronization. Here we have to move on to a different tool to model the dynamics of the hadrons. So what we are looking for is imprints from the initial geometry of the system in the transverse plane. So the longitudinal direction will be taken into account in the Bjorken model somehow automatically, that I don't have to consider explicitly. But the transverse plane geometry I have to put there in some form or another. So the idea is the profile of the initial state also exhibits some kind of eccentricities. Here are some examples. This is ellipticity, this is triangularity, quadrangularity. These are geometric. So as I mentioned at the beginning, these geometric deformations of the initial state will lead to deformations in the momentum space of the emitted hadrons at the end. And those deformations are measurable in the detectors and give rise to various flow harmonics. This is again a depiction of the heavy ion collision experiment. So basically the collision takes place and the fluid phase and everything that I told you about takes place in an infinitesimal point in this calorimeter that you see here. And from that onwards, we have hadrons. And these are trajectories reconstructed for the hadrons that reach the detector somewhere here on the cylinder. Again, the plot which shows the existence of the harmonic and therefore the existence of flow, and therefore the fact that there was quark gluon plasma in this very tiny region, which is not visible on this plot. This is again the plot I showed you, how you get from almond shape to this kind of distribution in momentum space. Here are some experimental results that have been reported by the CMS collaboration a long time ago, showing the V2. This is basically elliptic flow. So just ellipticity that is depicted in this form. Measured for emitted hadrons from a heavy ion collision. This was lead done at 5 tera electron volts. So the kinetic theory description involves the relaxation time approximation that I've put again here. We have equilibration towards the Bose-Einstein distribution, 42.25 effective bosonic degrees of freedom. And here is the initial state. So as I told you, there is no longitudinal pressure, therefore this slot is 0. And we have two slots here that correspond to the transverse pressure on the x and y directions, which have equal weight in the initial state. Here is an energy density profile, which has to be supplied as initial data for our simulations. So one aspect of relaxation time approximation, also if you go in the massless limit, where the particle constituents basically are ultra relativistic, is that the whole system is described by a single parameter, which is called opacity, that measures total interaction rate. This is what a realistic initial profile looks like, generated with some tool called Trento. It's an initial conditions generator, freely available. So what we need to characterize the system is basically this opacity parameter that depends on the shear viscosity, its ratio to the entropy density, and two more numbers. One is the system size, or its transverse size, which represents the root square mean radius. And here is the energy per unit rapidity available in the whole transverse plane. So it's integration over the transverse plane of the energy density. And this tau zero is there just to account for the fact that the rapidity bins are increasing in time. It's basically required in order to have a well-defined rapidity bin. So the problem with hydrodynamics appears when there is not enough time between collision and freeze out. If the system is small, so if the system is small, then it will fall apart more rapidly. It will have less energy to begin with, and it will cool down and go to free streaming in a much shorter time scale. In this case, we cannot speak of a really hydrodynamic phase of the system, but rather of a dilute expansion. So that's the problem. That's the regime where hydrodynamics will face difficulties if we don't really have equilibration before the system starts to hadronize. So this plot will tell us many things about applicability of hydrodynamics. Basically, this is a representation of the so-called attractor in this kind of systems. Here we have the ratio between longitudinal and transverse pressures. I told you that the system, as it's at the early times, is not able to sustain longitudinal pressure because of its rapid expansion, and therefore this ratio is equal to 0. But this curve here corresponds to kinetic theory. So that's the RTA, this solid line. We have another curve here, which is below 0, that corresponds to hydrodynamics. Simply, the theory of hydrodynamics is not able to correctly emulate what happens in such an out of equilibrium state. Where we see this discrepancy between the two curves, the dash curve and the solid curve, is where hydrodynamics is making a mistake, one which you can even quantify by looking at the distance between these curves. We also have here an example why these two curves are important. These are called attractor curves, because if you start the system anywhere else in this, let's say, ratio of longitudinal transverse pressure, it will quickly decay onto the attractor. So it doesn't matter actually how you start the system, simply that this longitudinal expansion of the system will pull any kind of initial conditions onto the attractor. And therefore, this is a universal evolution that takes place at early times. Also, there is a comparison of kinetic theory with bumps. You see that bumps with the circles is on top of kinetic theory, RTA. So therefore, RTA is a good tool to study these kind of systems. I will skip this slide. What I want to show you is that what hydro is doing in initial stage, so pre-equilibrium, is it does this kind of unphysical increase of transverse plane energy. Kinetic theory keeps the transverse plane energy constant because it's free streaming. So during free streaming, there is no loss of transverse plane energy. But hydrodynamics, because of its problems with out of equilibrium systems, will do this kind of unphysical heating of the system, which leads to a significantly larger transverse plane energy when equilibration starts to take place. So that's why we propose scaled hydro. Basically, it's a recipe to how to account for this unphysical behavior in hydrodynamics. So that's the green curve here, and the scaling is done such that at late times, hydro will fall on top of kinetic theory. So this is the regime where hydro becomes applicable because the system has equilibrated. This is just a depiction of what happens. So kinetic theory, basically, you can see this blob here is high energy, stays almost the same. But in naive hydrodynamics, this blob becomes even brighter. So it has become hotter. And in scaled hydro, the initial blob is dimmer because hydro will increase its energy to what kinetic theory has here. So this is basically the summary of what happens if we now measure the late time energy in the transverse plane. So after the fireball has fallen apart, the system is ready to hadronize. We have a frozen energy which is left in the transverse plane. Then we have kinetic theory shown with the black line. Here we have our scaled hydro, which agrees very well with kinetic theory. But as we decrease opacity or we increase shear viscosity, meaning that we make the system more towards the dilute limit or towards the transition regime, there will be some discrepancy. So you see here that the hydrodynamics is detaching from kinetic theory. This is the scaled version, and it does something wild at really low opacities. This can be seen also in elliptic flow. That's the smoking gun evidence of quark-gluon plasma I told you about. So one of the most important flow observables. Simply, hydrodynamics will detach from kinetic theory at small opacities. Here I put a band that tells us where QCD is expected to live. So QCD gives a shear viscosity of larger than 1, but not much larger than 3. So basically here it ends. Therefore, in the QCD relevant regime, hydrodynamics is reasonable. But this is done for lead-lead collisions at LHC. So that's the low band here. Lead-lead has an expected opacity of 5.7. If we now collide lighter ions, for example, oxygen, then we are already below the applicability of hydrodynamics, and therefore in the transition regime where hydrodynamics is expected to make some mistakes. Alejandro, I have to ask, how much time do I have left? I have some more slides, but I can also stop here.
Minus 5 minutes. So
minus
I guess
5.
if you
Perfect.
can wrap up, that would be great.
Okay. So this is a good point to wrap up. I have some more slides here. So this is event-by-event simulations that we've done to probe this discrepancy between kinetic theory and hydrodynamics, and some comparison to Atlas data showing basically some universality arguments for the flow response. But I will skip all this and just go to this slide to highlight that if you are interested, you will, of course, find my slides on the lawphysics webpage. You can click on these links and download the code and play with it as you wish, as you please. So this brings me to the conclusion. I wanted to point out that hydrodynamics is challenged for systems that are out of equilibrium. Kinetic theory can be used as some kind of baseline, some kind of theory that accounts for systems arbitrarily away from equilibrium. But in order to solve kinetic theory, we need some shortcuts. And the shortcut is relaxation time approximation that does a good job when comparing to a more realistic solver for the Boltzmann equation. And therefore, it's a relevant comparison of hydrodynamics to RTA. We have seen that hydro deviates from kinetic theory in small and dilute systems, underestimating the flow. And therefore, it may be unapplicable for small systems. So oxygen, proton, lead, proton. And these ones I haven't covered, but I leave them here for you to read. So I hope I still have some time to answer some of your questions. Thank you.
Thank you, Victor. Let me check if there are questions on the YouTube. In the meantime, if someone here in the call wants to ask a question, please go ahead. Let me just, while I go to YouTube and the other.
Yeah, I have a question.
Go for it, Lennox.
So first, thanks for the talk. It was a very nice talk. So I was wondering if all theories of relativistic hydro are bad far from equilibrium, or if there's a hierarchy of which are better or worse as you deviate from equilibrium.
That's a very good question, and one that people are striving to find a positive answer to. Personally, I would first advertise so-called anisotropic hydro. Its most recent incarnation is called VAH, viscous anisotropic hydrodynamics. And basically, this theory originates from this discrepancy here. So the idea was to allow in hydrodynamics, at the level of hydrodynamics, for the pressure to become anisotropic. What viscous anisotropic hydro does is it adds to this cocktail of pressure and anisotropy also the relevant viscous terms. It's a rather novel extension of anisotropic hydro, which is being now heavily tested in realistic scenarios. And myself, I have also worked on in this direction. And recently, I have a publication that compares viscous anisotropic hydro and to kinetic theory. And the conclusion is that this discrepancy that you see here is milder for viscous anisotropic hydro, meaning that its applicability is pushed to lower opacities. So if I would put viscous anisotropic hydro, then it would agree with kinetic theory, let's say, down to opacity of approximately 1. And in this plot, it's basically good also for P-led collisions, maybe would be challenged by PP collisions.
I see. Thank you.
Yeah, I don't see questions here in the chat. Victor, on the scale hydro that you propose, why you cannot scale it to like to go more up or like to compare to the other one? Like
so the idea
here, for
of the
example,
scale,
for the, yes. So it's also rising as the hydro, which was the problem, but it's rising from below. So in some sense, is there a way to like make it also not
Can I
rise
also
in
add to
time?
this? Add to this question as well. So could you explain also what exactly you're rescaling here?
Yeah, so there is a mathematical reason why these hydro curves are sloping upwards. And that's related to what hydro is doing in the early times. So I put here just a summary of the equation. You can find this by studying its attractor evolution. So what happens is in kinetic theory, we have this product, tau energy density constant, that is basically saying that this transverse energy is a constant, transverse plane energy. But in hydrodynamics, it's rising as tau to a small exponent, but small but non-zero exponent, tau to 0.07. Simply, it's properties of this second order hydrodynamics that we've been looking at. If you have a different flavor of hydrodynamics, then you can have a different exponent there. And anisotropic hydrodynamics will, of course, have also exponent 0. So in anisotropic hydrodynamics, this unphysical behavior is not there. Now, to answer your question, Alejandro, this scaling works brilliantly if the system enters this pink band here. So you see that here the green curve and the blue curve agree. They start to agree, and then they stay in agreement all the way to the end. This is transverse expansion here. This is a logarithmic scale from really small times. This is a time comparable to the system size when the system starts to fall apart. And basically, the plateau here tells us the late time transverse plane energy. The problem which hydrodynamics has is if this region, hydrodynamization that is shown with this pink band, is pushed to the right, because the system is in pre-equilibrium or out of equilibrium for a longer time. And this happens for systems that are more dilute or smaller size, have less energy, and so on. If this is pushed too much to the right, then already transverse expansion sets in before the two curves have merged. And then the two curves stay, there's this gap which will persist, and hence is the reason why this purple line is bending downwards. Simply, hydrodynamics doesn't have enough time to make up for its decrease due to the scaling procedure. If there is no scaling procedure, then this is basically the result of naive hydro, unscaled. Simply, it's off. It will have a larger energy than what it should be.
Thank you. Okay, I don't see any question. Anyone here in the call want to ask a question? Okay. If not, then you know where to find Victor, and we thank him again for this nice introduction of the field. And for everyone, stay tuned for the next Law Physics webinar. Thank you, Victor, for this lovely presentation, and we'll see everyone in the next one. Thank you.
Thank you very much.
And okay, we are not live. Thank you, Victor. This is